So here we're going to prove that the median of median is a good median, which is a fun thing to say. And this is one of those proofs where, a drawing is all you need, but, the formal proof is slightly, looks more frightening than it is if you just understand what the figure says. Okay, so here's what the idea of the algorithm is. We take the array and we split it into columns of size 5. For every one of the columns, we found the median. This is the yellow elements, right? And then what we did, we found the median of the yellow elements, and we used it as a pivot, right? And that was the algorithm. Now, the claim is that there are at least this number of elements, let's just say 3/10 of n elements, that are smaller than this median of medians, right? Or another way of saying it is that our median of median is going to be a good pivot. It's going to be roughly in the middle. Okay, so let's prove it. So the trick is, you need one simple trick. So the trick is that after we find the median of the medians, let's reorganize, let's shuffle all the columns such that all the elements that their medians is smaller than the medians are to the left of the median, right? We are just sorting the columns. You can just think about it as sorting the columns by the value in the yellow row after we sorted every column. Again, this is just conceptual. The algorithm is not going to do that. It doesn't need to. Okay, so as such, all those yellow elements to the left of the pivot are smaller than that. Similarly, all the things that are to its right are going to be bigger than it. Right? Okay, now to remind you, to compute the pivot of every column, we just sorted it using brute force. We didn't even try to be clever about it, which means that the order of the numbers is increases as we go down, right? So this number in the top left corner is in fact smaller than the next element in the column, which is smaller than the median of this column. Similarly, like that, right? So we have the following property that if you think about ordering as arrows, things are increasing when you go down, and then the medians going to the right, they're increasing. Now, notice that we don't know, for example, what the relationships between the first number and second number in the top row. We don't know that, but we do know one thing, right? We know that they're smaller than the pivot, right? Why do we know that? They're smaller than the pivot in their column because, well, they're above it. And this pivot of this row is smaller than B, the pivot of pivots, right? Because we copied all the columns that had smaller pivot to the left of this, right? So this implies that all the elements here, right, all the elements showed in the bottom figure, right, they are strictly smaller than the pivot, right? And they're roughly a quarter of the array, right? Roughly a quarter of the array. It's not quite a quarter. You have to be a bit more careful. So let's be a little bit more careful, right? There are n over 5 columns. Let me ignore floors and nonsense like that. The median is going to be the middle element, so there's going to be half of them. So the number of rows here is going to be n over 10, right? N over 10. Now, there are n over 10 columns. Each one of those columns contains 3 elements smaller than the median, right? And of course, except for the last column of the median itself, so you get some noise. So -6 takes care of this noise, right? It just says, oh, ignore this column, ignore floor and stuff like that, which we shouldn't care about, right? Now, it's kind of interesting to look at this matrix and ask, okay, so all the numbers that are bigger than the median, the median we just maybe red is not a good choice. Let me use blue. All the numbers that are bigger than the median of medians are the blue numbers. Okay, now if you think about it a bit, all the numbers that I'm drawing here as green, from green, all those green numbers, we don't know how they relate to the medians of medians. They can be smaller, they can be bigger, it doesn't matter, right? What matters is that all the blue numbers, which are roughly a quarter of the element of the array, or slightly more than that, are bigger than the pivot, and similarly all the red elements are smaller than the median of medians. So the median of medians is really going to be pretty much in the middle, right? It's going to be between 3/10 of n and 7/10 of n. If you think about its rank in the array. Here I'm ignoring, numbers. Okay, here's the formal proof. We just repeat what I just said, so we don't need to go over that. And now, the complement of the lemma is the proposition that there are at most 7/10 of n element plus 6, whatever, that's noise, that are bigger than the pivot, right? And similarly, there are at most 7/10 of n of 6 elements smaller than the pivot, so the pivot is really in the middle, and that's what we really need to prove the running time of the median of median algorithm, which we will do.